Welcome. Today's notes worksheet is entitled Real Zeros of Polynomial Functions Day 3. And so this lesson offers us an opportunity to extend our discussion with zeros of functions. And we're going to be taking a look at a pretty complicated and abstract addition to our concepts here. So we're going to look at something called Descartes' rule of signs. And it's named after René Descartes, a French philosopher and mathematician who I believe lived around the early 1600s. And so what we're going to take a look at, as it says on your sheet here, the nature of real zeros. And as a matter of fact, just as I'm kind of thinking about it, can everyone kind of underline that piece? So real zeros, which means basically we're talking about zeros that are either rational or irrational. So those are the types of numbers that make up, that fit under the real number umbrella. And so that's what we'll start to take a look at here today. And so I laid out as best as possible here a way to kind of go through it and see some connections and identify some patterns here. So I have a set of, let's see, and let's actually just number these just so I have a reference. So I believe I've got 7. There they are. So 7 functions that we'll take a look at there. And what Descartes found was that there is a relationship between the number of sign changes as you move left to right for a polynomial function in standard form, so the number of sign changes, and the number of real zeros, be it either positive or negative. So I think the way we'll do this is to take care of the top part of your sheet first and kind of fill in column by column. Then we'll go ahead and transition to the bottom of your worksheet and fill in column by column. And in each case, we'll go ahead and draw a conclusion on this. And then obviously we'll see how it fits into what we've been talking about before and put it all together as we do a couple problems on the back. So let's go ahead and get started. The good news is this column right here where it says the number of sign changes is a relatively simplistic one. And so here's what I'm thinking. For number 1, basically all I'm looking for, everybody, is as I move left to right, and again it has to be in standard form, which it just so happens all of these are, basically all I'm looking for is how many times the coefficients change from either positive to negative or negative to positive. So in this case it goes positive 4 to negative 6, that's 1, negative 6 to positive 1, that's 2, and positive 1 to negative 3. So that's 3. 3 sign changes. Okay, so that would be the case right there. I'll do one more and then maybe ask you to pause the video and knock out the remainings, I guess the remaining 5 it would be, and then we'll see where we are from there. But let me do number 2. So in this case it looks like I'm going from positive 5 to negative 6, so that's 1, and then negative 6 to negative 4, well that's not a sign change. So I only had a sign change from here to here. And so as a result, everybody, it looks like 1 sign change would do. All right, so do you mind how about pausing the video for just about a minute or so, shouldn't take you too much longer than that, and see how many sign changes for each of the remaining 5 functions you can find. Okay, well let's see how you did. So when I did mine, I'll just do one more kind of up here. 1, 2 sign changes for this one. And then let's see, I'm going, looks like 2 sign changes for this one. Again, just working left to right, how many sign changes? I have 3 sign changes right here. And then no sign changes right there. And last but not least, it looks like 1 sign change right here. Okay, so now again what Descartes found was that there was a connection between the values in this column right here and the values in this column right here. So first and foremost, let's be clear about one thing because we're going to do this graphically. We're going to be looking for the number of positive real zeros of our function. I don't want to know the actual zeros. All I want to know is how many. And if we're talking about positive real zeros, remember, in essence, everybody, and I'm just going to draw a coordinate plane here, just kind of thinking out loud with this. Remember, real zeros show up as x-intercepts on the coordinate plane. And if they're positive, that would mean obviously to the right of our y-axis. When we hit the bottom of the sheet, by the way, we're going to be looking at negatives. That would be to the left of the y-axis. So what we're going to be looking for here, everybody, is how many times we have a positive real zero. So somewhere from there out to infinity. Okay, well, we're going to need a graphing calculator here. I'm going to do a couple with you and then maybe fill in some of my blanks and ask you to kind of do some work on your own as well. And let's see what happens. So everyone go to the y equals, and let's just start out with the top one. Very simply, I have a 4x cubed, and then minus 6x squared plus x minus 3. All right, so I'm going to type that in. I'm going to just zoom standard when I get a chance, so zoom and number 6. And again, all I'm concerned about is how many positive real zeros there are. And in this case, I'm hoping everybody sees it looks like there's just this 1, somewhere in between positive 1 and positive 2. But that would be the case right there. So 3 sign changes, keep an eye on that, and 1 positive real zero. Okay, great. I'll do 1 or 2 more here and then kind of fill in some of mine. And then ask you to do the same, just kind of pause the video on occasion and do some. So I don't mind knocking out a couple others though while I'm here thinking about it. So 5x cubed, how about minus 6x, and minus 4. Same issue. Just go ahead and hit graph at this point. Graph them, similar looking cubic function as a matter of fact. And it looks like, of course, 1 positive real zero. Okay, I'm going to do one more here. So I'm going to bring my calculator up, and I'll do that third. And looks like in this case, I have 3x cubed. All right, so let me clear this out and type this in. 3x cubed minus my 4x squared plus 3x and plus 7. Okay, everyone, so now I'm going to go ahead and graph that as well. And in this case, an interesting looking cubic, at least on this window. But I do not have any positive real zeros. Here are the positives out here. It looks like this one real zero happens to be negative. Kind of keep that in mind for the bottom part. But essentially, there are no positive real zeros. All right. So you see, I'm hoping at this stage you kind of see what I'm after. Again, just graph each one and how many positive real zeros do you see. Okay, everyone, if you don't mind, can you pause the video for me and do the remaining 4? So please get comfortable with this graphing calculator. We're going to be doing a lot of this over the unit in terms of being able to analyze and find zeros of functions using the calculator. So please take a moment and do that, and then come on back. Okay, well, when I did this, I ended up getting 2 for this one. I ended up getting 3 for this one, as a matter of fact. And then 0, and then 1. And so now, obviously, what we want to do is take a look at the 2 columns. As I had mentioned, there is a connection, or at least Descartes discovered a connection between the number of sign changes in a polynomial function and the number of positive real zeros as a result. And so I guess the conclusion that we can draw is based on those 2 things. Now, I guess I would, of course, if this was a class, I would certainly ask you and see if we can come up with it together and have that discussion. But take a look, and I guess you can start to see a couple scenarios at hand here. Number one is in some cases they're identical. Here, right, one sign change, 1 positive real zero, 2 sign changes, 2 positive real zeros, 3 and 3, 0 and 0, et cetera, et cetera. So in many respects, and not all functions by any means, but for many of these functions, the number of positive real zeros is the same as the number of sign changes. So let's start with that. So the number of positive real zeros and then here's what I have, is equal to the number of sign changes and then what I need you to do, everybody, is put a big or right there and underline that. And then what is the or? Because again, Descartes found that that can be the case. They can be equal. But or, and then how would you fill in this piece? Because it's not always. And if you sort of see here, now these are somewhat limited functions. I think I went cubic on all of these. But basically you see that I had 3 here, but only 1 positive real zero. 2 here, but no positive real zeros. So you kind of see that they're sort of down by 2 as a result. But we're going to extend on that just a little bit. But I'm hoping everyone see it looks like it decreases by 2. So here's how I'm going to amend this, and then we'll talk about this in just a sec for some of the bigger ones. But basically you can see it's either that or less than that. And here's what I'm going to write. By an even number. Okay, and then as I said, I will elaborate on exactly that piece. Here you saw they're less than that by 2. And that can certainly occur. So what if we had a bigger polynomial? And again, give me a moment just to illustrate this piece. So basically, what if we had one, don't write this on your paper, but what if we had one that had 5 sign changes to it? Well, basically what Descartes is saying with this one is that as a result, there could either be 5 positive real zeros, or, and then this is the piece down here, less than that by an even number. So what that means is it could be either 5 or 3, because that would be less than that by an even number, or 1. That would be less than that by 4, which is an even number. So that's what this is saying right here. If there were 5 sign changes, then there would either be 5 or 3 or 1. Obviously, the more sign changes, the less definitive Descartes' rule of signs becomes. The fewer sign changes, the more definitive it is. So for example, just one more, just in case you're still not with me on it. What if we had 6 sign changes in a particular polynomial function? Descartes would be saying for this one that you could have 6 positive real zeros, or you could have 4, or you could have 2, or you could have 0. Okay, and that's what these are, less than that, less than the 6 by an even number. That's the idea. Okay, and we'll kind of develop some ideas based on that premise as we go through and do some examples together. All right, so I'm hoping everyone's okay with that piece right there. We have the top part of your notes worksheet taken care of, and that's great. So the number of sign changes and the number of positive real zeros, there is the connection that Descartes discovered. All right, now the negatives require just a little preliminary work. So let's go ahead and take care of our business here. So this is the case that we're going to have to deal with the negatives. Before we can actually go ahead and graph those original functions right there, I have to do a little algebraic modification on it. And so we've seen this before, and this notation right here says f of negative 1x. So what I'm going to do, this is an input change, everybody. What I'm going to have to do first for a moment is take all of my functions and replace the inputs from x to negative 1x. And so what we're going to do, I'm going to take just a moment and jot a couple things down and then erase it and then kind of shortcut this for you. But basically what we would do in that top function, I'm going to do that top one first. Again, bear with me for a moment on this. Just watch the screen for a second and let's see it. So basically what we would do for that top function is replace all of the x's with negative 1x. So that first function would look something like this. So plus negative x, and then minus 3. Now watch what happens with this, because I'm going to try to get us to do a little shortcut so this can be a 5-second process as opposed to a 30-second process. So does everyone see, first of all, when I cube something like negative 1x, cubing negative 1 makes it negative 1. And so as a result, this becomes a negative 1 when I remove the parentheses, which as a result will change that coefficient right there. So I end up getting, I'm hoping everybody sees this piece, I'm hoping that you would see that it's a negative 4x cubed. But when I square a negative 1x, squaring negative 1 just makes it back to positive 1. And so that does not change this coefficient right here. So this would end up being minus 6x squared. So again, when you raise a negative 1 to an odd power, it's going to change the coefficient. When you change negative 1, well, we change it to an even power, essentially it does not change the coefficient. And then so this would be a minus x and then a minus 3. And so this, everybody, would be that f of negative x right there. And then obviously, guys, we're going to start talking about the number of sign changes. So let's go ahead and just write a little shortcut for this, as I said, so we can make it more of a 5-second process. But basically what we want to do here is input negative 1x for all these functions and rewrite and see what we end up getting. So here's what I wrote on my paper basically. So for an odd degree, we change the coefficient. and in an even degree, keep the coefficient. Okay, hopefully you can kind of read that in place, and then I'll show you a couple of these and show you how quick it can be. And then as a result, we'll kind of, I'll pause and ask you to do a few as well. So I'm thinking I'll do the first 3. How about that? And then ask you to do the last 4, and then we can sort of just make sure everybody is on the same page with this. So I already did that first one, but let me do it again, just kind of using the shortcut there. Anytime I see a term with an odd degree, I change the coefficient. I change the sign of the coefficient. Anytime I see a term with an even degree, I keep the coefficient, whatever sign it is. So for example, the top one there, let me read it one more time. Everyone take a look at your sheet. It's f of x equals 4x cubed minus 6x squared plus x minus 3. And if I was to do f of negative x, again, what I would do is change the terms with an odd degree, keep the terms with an even degree. So change the odds, keep the evens. And it's that quick. Okay, I'm going to do the next one. Everyone take a look at the next one with me and see how quick this ends up being. That was 5x cubed minus 6x minus 4. So anything with an odd degree, I change. So negative 5x cubed now. Minus 6x changes to a plus 6x. And minus 4 obviously just stays the same. Okay. How about one more that I'll do with you? Everybody look at the third one. And it's f of x equals 3x cubed minus 4x squared plus 3x plus 7. Again, one more time. Anytime I see a term with an odd degree, I change the sign of the coefficient. Anytime I see a term with an even degree, I keep the sign of the coefficient. And so here's how it goes. I would change the cube, so negative 3x cubed, keep the squared, so still minus 4x squared, change the linear, so minus 3x, and obviously sort of x to the 0 on the back, even though we don't think of it that way, but just the constant stays, obviously. And there it is. All right, everyone, would love for you to take a moment, see if you can knock out these. Try to do each one in about 5 to 10 seconds. Don't want it to take too much longer than that. See if you can knock out the remaining 4 for me. All right, well, let's see how you did. I'm going to go ahead and write what I did up on my board, and then obviously we'll relate this, find the number of sign changes, and then regraph and go get those negative zeros. So here we go. I have for number 4 up there, this piece. Excellent. How about number 5? I get this right here. 2 more to go. Number 6. And last but not least there, number 7. Okay, perfect. So in order to talk about the number of negative real zeros, here we are over here, everyone, the number of negative real zeros of f of x, and by the way, underline that, we're still graphing our original functions when all is said and done. We did have to do, again, a slight algebraic modification to kind of see the connection here. So now, everybody, we're going to relate these 2 columns together. So it's the number of sign changes for this. So I should actually write in here number of sign changes of f of negative x. Let's go ahead and now actually all jot that in there. So the number of those sign changes, and then the number of negative real zeros of our original function, of course. Okay, guys, well, let's go ahead and take a look. Let's run some sign changes. I'll do a few, you do a few, and then we'll go ahead and graph and come up with our conclusion on this. So let's just run left to right here, everybody. Number of sign changes, 0. Okay, let's keep going. Number of sign changes looks like 1 and looks like 2. Excellent. Let's keep going here. Nope. Nope. Yes, 1 sign change. All right, so does everyone see? Just now run left to right, if you would, and figure out the number of sign changes for this modified version of our function. Okay, again, everyone pause for a moment, see if you could pull that off for me. And then let's go ahead and get our remaining ones in place. All right, let's see how you did. So for this one sign change is all I see. This one, everybody, no, no, nope. So I have 0 sign changes. Let's see here, 1, 2, 3 sign changes on that one. And then last but not least, 1, 2. 2 sign changes there. Okay, so now what we want to see is the connection between this column right here. And by the way, it's going to be very, very similar to what we saw at the top part of your page. So let's keep that in mind. And here's the thing. What we're going to do is grab the calculators again at this stage, and we're going to graph our original functions. So the 7 originals, I'll probably do the first few, and then you'll do the last few. So you can hang tight for a sec and then watch me do a couple of these. But remember, the idea is we want to graph the original functions, not the modified version. That's just to help us talk about the relationship between the number of sign changes and the number of negative real zeros. So I'm going to type in the original function there. Everyone take a look at the top of your page, and that is the function obviously I'm typing in. We saw that there was one positive real zero to this, and now I just want to see how many negative real zeros there are. And there's the one positive, as we saw already, and I do not see any negative real zeros. Okay, perfect. So everyone, 0 right there. And by the way, look, so the number of sign changes of this and the number of negative real zeros of the top there of the original function. Okay, let's keep it going. I'm going to bring it up again. I'll do the next one. So that was, from the top, 5x cubed. And let's see, minus 6x, and how about minus 4? I graph, and once again, in this case, looks like no negative real zeros. So as you can see, not a 1. In this case, notice what we had, 2 sign changes on this f of negative x, but no zeros of the original function, no negative real zeros. What would be your guess here, by the way, for this next one? There is 1 sign change on this f of negative x. How many negative real zeros do you think we're going to get of our original function there? And if you've been kind of paying attention, shouldn't come as a great shock when I go ahead and type this in. So let's see, this was 3x to the third and minus 4x squared plus 3x and plus 7. Alrighty, I hit graph, and I remember seeing this one. There it is, everybody. There's your 1. 1 sign change. Again, Descartes' pretty definitive on that, obviously. Okay, everyone, so I'll ask you to do the remaining 4. Just one more time to be very clear. You are typing in the original function. Do not type this in. This is not quite right in terms of what we're looking for. We want the number of negative real zeros of our function, of the original function, from the 7 that are above. All right, everyone, please, if you would, type the remaining 4 in, fill in that, and then come on back and then see how you did. Okay, well, I got 1 here, and that makes pretty good sense. There we go, 1 sign change, 1 negative real zero. This one, no sign changes, so no negative real zeros there. This one, as it turned out, this one wouldn't be quite as definitive, but with 3 sign changes, there were actually 3 negative real zeros. And here, again, not quite as definitive, but in this case, it looks like there were 2. Okay, good. So you could see a very similar pattern here. For the most part, they're the same, but not always. And in this case, you see that this is less than that by 2, or less than that by an even number. All right, so let's be clear on this conclusion, and then we'll do our few problems on the back just to make sure we're feeling good about it. So the number of negative real zeros and this is, of course, of our function, everybody, so let's be clear about that, of f of x, is equal to the number of sign changes, and here's where we do have to be careful as well. So the sign changes were on that modified version, so of f of negative x, okay, or, and then here we go, one more time, less than that by an even number. So same situation, everybody. For example, just very quickly to re-emphasize what we looked at above, if I had 4 sign changes on this f of negative x, what Descartes would basically say with that one is you could have either 4 negative real zeros, or 2 negative real zeros, or 0 negative real zeros. So less than that by an even number. And there is a reason that it goes down by 2's, by the way. As we are talking about real zeros, think about the other type of 0 that I have left out, which we will certainly pick up on in the next couple days. So we'll potentially talk about that piece a little bit today, but you'll definitely see that idea come up. Well, everyone, I think the best thing to do is to just go through some examples and see it all come together. So now we have some different ideas, concepts, theorems, etc., and see how each individual one sort of fits in the overall context. And let's see. Let's make it work. Okay, example 1, everyone. Looks like I've got a nice, pretty basic cubic here. And, you know, we haven't talked about this explicitly. This will come up in the next couple days. But I think we know this intuitively, everybody. With the cubic function right here, how many zeros am I going to ask you to find? Well, definitely every cubic is going to have 3. So let's put that in place right there. Now, everyone, if you would, let's go ahead and connect B and C. So B and C, everybody, will be the phrasing for Descartes. And it says how many positive real zeros, how many negative real zeros. So just off to the side there, if you want, Descartes' rule of signs. Okay, so B and C, that will be exactly what we just took quite a bit of time on and actually sort of looked at. So anyway, let's go ahead and get B. I'm going to do some work down here just as a result. I have some room on my paper, on my board, I should say. Hopefully you have some room on your paper to do this. Okay, guys, well, let's go for it. So B very simply is this piece right here. I'm going to go ahead and just rewrite my function. You don't have to if you don't want to, but basically the number of sign changes, I go 1, nope, no sign changes at all. So as a result, 0 sign changes, and shouldn't be any positive real zeros as a result. So Descartes is very clear on this piece. For this particular function, there are no positive real zeros because there are no sign changes as we move left to right. Okay, now if I do part C, what I have to do is that quick f of negative x. So as I said, this one just requires a quick modification. Then we can start taking a look at it. So anyway, here's what I have. Change the odds, keep the evens. Change the odds, keep the evens. And so anything with an odd exponent, the sign in front changes. And now, everyone, let's go ahead and see the sign changes here. 1, 2, and 3. So 3 sign changes, everybody, which means, now, just be a little careful, not quite as definitive. So what Descartes is saying that there will be either 3 or 1 negative real zeros for this particular function right here. So let's kind of talk about that composition real quick, and then we'll get into little p over q. So first and foremost, we do know that there are 3 zeros to this function. That composition can go a couple different ways here. Descartes is saying that it will either be 0 positives and 3 negatives. That would make up the 3. Or, everybody, it would be 0 positives, 1 negative, and what would the other 2 have to be? What's the one that's now not accounted for, which, and we'll see this more explicitly, but I think intuitively we know always shows up in pairs, the complex numbers that are not real. And so in the imaginary number system, essentially. So it's either going to be 0 positives and 3 negatives, or 0 positives, 1 negative, and 2 that are complex, not real. So let's see. Let's see how it does play out. Hey guys, just for this piece right here, letter B, want to write a little p over q. That's the phrasing, of course, we saw for possible rational zeros. And I'm hoping everyone can knock this out pretty quickly. It looks like plus or minus 1, plus or minus 2, and plus or minus 4. And notice what it says on your paper. It says find the zeros of this function. And so what we now did is kind of narrowed it down here to some possibilities. If there are some rational zeros, they have to be one of these 6 numbers, 1, -1, 2, -2, or 4, or -4. And so what we would do is try them out, and hopefully we get a hit, and we can use that to break our polynomial on down. Well, I would argue that P over Q did a nice job here, down to 6. I guess you could say that we could even break it down even further. So think about this in terms of testing numbers now with synthetic division. You could probably tell me that 3 of those 6 numbers right away will not work without even testing with synthetic division. And which ones? Well, if you think about it for just a second there, 1, 2, and 4 simply can't work. Because if you look at what we found out already, Descartes tells us for this function, there are no positive real zeros. So 1, 2, and 4 are out of the mix. Simply, they won't work. So we don't even have to try them with synthetic division. We know they're not even possible. So I guess the thing to do now is let's try one of the negatives. I'm going to go with -1 and cross my fingers. So remember, guys, it's just running the synthetic division across here. And we're at cubic right now. It'd be great to get down to quadratic. Let's go ahead and see if this divisor, which would be x plus 1, if it divides evenly into that cubic. So let's go for it. Got that. And, all right, I have a winner. Beautiful. So I knew the 1, 2, and 4 would not work. I tried -1 right there and hoped for the best, and it was a winner. And so everybody at this stage, now what we do is set our quadratic. That's our comfort zone, everybody. We set that quadratic to 0, and we solve. So this one does not factor, by the way. It looks like the -2 and the -4 are not going to work. So let's go ahead and get the other 2. Everybody, I'm going to complete the square. Be great if you can maybe pause the video and come on back and see how you did with completing the square. Should be comfortable with this piece. So remember, that's a little 1 sitting out in front here. So we take that 1, divide it by 2, and then square it. So 1/2 squared, everybody, is 1/4. And so 1/4 right here. The whole reason, of course, for completing the square is because of the way it factors. Square of a binomial, this should be x plus 1/2 times x plus 1/2. Now, everyone, the right-hand side, I'm going to have to simplify here. I like dealing with it as an improper fraction. I think it works a little cleaner. So I'm just seeing -4 plus 1/4. This, to me, reads as -16 over 4. That's what -4 is. So -16 over 4 plus 1 over 4 should be -15 over 4. Take a look at that. Make sure that clicks for you. It's time to undo the square, of course, everybody. So let's undo and undo. I get x plus 1/2 equals, don't forget the plus or minus, everybody. Now, square root of 4 is 2. It looks like I'm dealing with the square root of a negative, so I is coming out, and 15 really can't be touched underneath the root there. And so as a result, I think that 1/2 will come over. Just be careful with this. When it does move over to the other side, it becomes a -1/2. Just please keep that in mind. A couple different ways to write this. We've seen this, of course, before. And that looks nice right there. So in terms of the zeros of this function, let's go ahead and write them in. Everybody, we saw -1 is a 0. And then -1 plus or minus I root 15 all over 2. And that's the nature, the composition of our 3 zeros right there. And notice Descartes was right on target with this. 1 negative and 2 complex but not real. So it ended up being this and this. No positives, 1 negative, and 2 in the complex number system. Okay, good. Let's move on to the next one. Let's see if we can develop a nice rhythm with this, everyone. It'd be great if you could work a little bit ahead. Let's see what we've got going. So how many zeros? It's cubic, everybody. We'll spell this out a little bit in more detail in the near future, but for right now, I think we all know 3 zeros for that. Everybody, Descartes, let's go ahead and run it by. So in terms of this one, I'm just going to do it straight up here now, just kind of looking at it. 1 sign change, 2, 3 sign changes. So that means they're either going to be 3 or 1 positive real zeros here. Now if I am going to do the negative real zeros, I do have to do that quick modification. So change anything with an odd degree, keep anything with an even degree. Change anything with an odd degree, keep anything with an even degree. And so moving across there, guys, how many sign changes do you see? 0. So similar situation to the last one, and cubics all have kind of a similar format here. In this case, Descartes would be saying that there are either 3 positives and no negatives, or 1 positive, 0 negatives, and a couple complex not reals. P over Q's, let's go ahead and run them out. How about 1, 2, and 4 again? Keeping those easy for you. And then I think we'll start to transition a little bit here. So it says find the zeros. And then rather than going ahead and just testing blindly with the synthetic and hoping for the best, this will be the first time we actually get to use the calculator to really guide us here. So we at least understand that if there are possible rational zeros here, it's going to come from this list. Rather than just testing one and then testing -1 and just, crossing our fingers every time, let's let the calculator sort of give us the ones that work. So let's go ahead and type it in, everybody. You with me. And -4 right there. I'll hit graph. And interesting. So I have a couple weird situations here, but let's see. This one definitely is sort of irrational. That's what I see, because it's sort of in between the 0 and the 1. And let's see here. I'm kind of hoping for the best. It's tough to tell. I could zoom in if I wanted, but I think I'm just going to go ahead and kind of look at my list here and try to get it going. So in this case, if you struggle at all with finding these zeros from the calculator, that's all right. Let's see. I'm hoping it's that 4. I'm going to either verify or refute that momentarily. There it is. So it was tough to tell. It looks like I had one right before the 4, but I also have one at 4 here. So I need a rational number in order to break this down. And so what this calculator now told us is one of those P over Q values works. It's +4. And so that's the one I'm going to use, everybody, to break this down from cubic to quadratic. So let's go ahead and do exactly that. Again, we're using the calculator, to sort of tell us what will work and what won't work. And in this case, obviously, we already figured out the -1, -2, and -4 were out because Descartes told us that would be the case. So it was either going to be 1, 2, or 4, hopefully here. And I didn't see the 1 or the 2. That's why I kind of focused in on that 4. Well, let's go for it. Bring down the 1, and let's confirm that up here. And there we go. We've got it. Okay, so the 4 is definitely one of those zeros. I did actually get that from the calculator. Now the other 2 were real zeros. They just happen to be irrational. So let's go ahead and set that to 0 right there. And let's go ahead and solve. So x squared minus 4x. Let's complete the square, everybody. And so I see definitely a +4 here, +4 here. This one's going to be easier than the last one, so that's nice. That factors beautifully to x minus 2 times x minus 2. This one is -1 plus 4, so that's 3. And everybody, if you would, on your paper, undo that square. Don't forget the plus or minus, of course. So plus or minus, and then square root of 3. And lo and behold, I think we get our other 2. Real numbers, by the way, just happen to be irrational. And so we'll talk about Descartes momentarily before doing our last one, but those are your 3 zeros right there. 4, and then 2 plus root 3, and 2 minus root 3. Now, by the way, and we saw this actually on the graphing calculator, if you take 2 plus root 3, you end up getting a positive real number. And if you take 2 minus root 3, you also get a positive real number. So in terms of Descartes, everybody, this is exactly what happened here. 3 positive reals, 1, 2, 3, and no negatives. And so Descartes was right on target again. Okay, let's do one more. Okay, so now we have a quartic, which means, everybody, let's get this going. Definitely it's going to be 4 zeros here. So let's see this piece. How many positives? How many negatives? All right, everyone, there's Descartes again. So tie B and C together if you would. And that's Descartes. So let's go ahead and run some signs across here. Nope. Nope. 1. I'm only getting 1. That's interesting. So as a matter of fact, as definitive as it gets, we should expect 1 positive real 0 here. Now in terms of the negatives, I'm just going to work down here. Oops. And let me just make sure I do that right for you. Remember the case, of course, everybody. Keep the coefficient on the even degree. Change the coefficient on the odd degree. Keep the coefficient on the even degree. Change the coefficient on the odd degree. All right, so there is your f of negative x, everyone. And let's go ahead and see how many sign changes we catch here. I've got 1, 2, 3 sign changes, which again means either 3 or 1 negative real zeros. So for this function, Descartes saying out of the 4, it's either going to be 1 positive and 3 negatives, or 1 positive, 1 negative, and the other 2 would be a pair of complex numbers that aren't real. Hey everyone, if I asked you to do a P over Q list, I know you could pull this off. Let me just run my list out for you. So this one gets a little hectic there. Something like that. That would be a lot to just test and hope for. So that's what I said. We're going to start using the calculator to help us break some things down. Okay, so this is another one that's a little difficult to interpret from the graph. I will definitely help you with that, and hopefully, in the future we can make them a little more clear for you. But essentially what we want to do here is x to the 4th. I have a plus 6x cubed. And how about plus 4x squared minus the 30x, and how about minus 45? All right, I hit graph, and yeah, it's a little convoluted in there. I could tell you a couple things that are going on with this, and we'll sort of move forward with it. Let me see if I can catch it here. Just curious. So I'm going to go to my 0 function there, and let's see. This is interesting. So I've got that. Let's do that right there and see what happens. There it is. And it just so happens, again, I'll lead this one, especially we've been talking now for over 40 minutes, so I want to start to bring this to a conclusion. But essentially that negative 3 right there happens to be a touch. What happens with this graph, everybody, it goes down, it touches at negative 3, comes back up for just a little bit, and then actually crosses again just in between the negative 2 and negative 3. I seem to recall that graph, having seen it before. So regardless, everybody, negative 3 is going to be our P over Q, and I'm telling you it's a double. It's a touch there at that negative 3. So there it is on our list. Let's utilize it, everyone. So here's what I have. Let's use the negative 3 right here and go 1, 6, 4, negative 30, and negative 45. All righty. Well, let's break this down from quartic to cubic, as we've been talking about before. So here we go. Got that. And beautiful. Remainder of 0, x plus 3 is a factor, and x plus 3 goes into this quartic this many times. X cubed plus 3x squared minus 5x minus 15. So this times this is the quartic. That's great. Now I'd like to use one of the other factors to break it down further. And it seems like I have another factor of x plus 3. And so I'm going to use that negative 3 again. The only reason I can use the negative 3 again is because it is a double from the touch on that x-axis. And so I'll use that negative 3 to break this down further. And get this right here. And get that. And let's see, 15 here. Beautiful. Okay, so the negative 3 is a double. Now the other two, let's see what occurs. Now I'm down to quadratic. No more p over q's left to deal with. It's time to just solve the quadratic. So x squared minus 5 equals 0. And looks like this is certainly a candidate for undoing the square, so everybody add the 5. Let's undo the square at this stage. And when I undo the square, everyone, looks like I get my plus root 5 and negative root 5 there. Excellent. Both irrational numbers, but both real numbers. And one is positive and one is negative. So let's see what we end up getting here. I got negative 3. I'm going to write this as a double, by the way. So negative 3 is a double, and then plus or minus root 5. So you're 4 zeros. Now this one counts twice. So in reality, everybody, let's see if Descartes was on target with this one more time. 1, 2, 3 negatives, right? So negative 3, negative root 5. 3 negatives. And positive root 5, 1 positive. Absolutely perfect. Descartes, once again, right on target with it. So start using the calculator, everybody, to break it on down. As I said, hopefully they'll be a little easier to interpret than what we saw in these last two examples. But once you find one, use the synthetic to break it on down level by level. When you get to quadratic, you're on your own. Okay, guys, doing great. Let's do just this last piece. I like this extra credit. I forgot about this one until seeing this sheet. I'm just going to read it and then have you go for it. So here we go. Seymour, the census taker, came to a farmhouse and asked the farmer for the ages of his 3 children. The farmer gave Seymour some clues. Number 1, the product of their ages is 72. Product means multiplication, by the way, everyone. So product of their ages is 72. The sum, addition of course, the sum of their ages is the same as the house number. And then Seymour said, he looked at the house number, he said, wait a minute, I still can't tell. Notice I bolded that, by the way. I still can't tell. So, number 3, the farmer then told him that the oldest child likes to snowboard. Then Seymour knew their ages. How old are the 3 children? So students ask all the time about this one, wait a minute, you didn't tell us the house number. Well, you don't need it. All the information is there, everybody. So read it over a little bit, see if you can figure it out. And if so, I'll throw some extra credit your way, of course. Hey, this was a lengthy lesson here. Hopefully I developed some of that Descartes with you nicely, and it sort of worked with some of the examples on the back side. Certainly ask questions if you have them, and thank you very much for listening.